Welcome back everyone, and in this video we want to start talking about neural networks, or how they're also called artificial neural networks, forward neural networks, multi-layer perceptron. Those are more or less all synonym in describing the basic architecture of a neural network. There are other architectures, and we will not discuss them in detail here, just that you heard about them, for instance recurrent neural networks or convolutional neural networks. Okay, why are we discussing neural networks? First of all, the neural networks are very flexible function approximations, or they can almost capture any kind of functional relationship, which is obviously a very good attribute because we're always trying to grasp functional relationships between feature variables and, for instance, target variables. Furthermore, neural networks, or at least the building blocks of neural networks, is something that you already heard about in this course, because the basic models we discussed in the beginning of this course, like the linear regression model, the logistic regression model, the softmax regression model, if you combine the ideas of those models, what you basically get is the architecture of a forward neural network. So hopefully, there is no big step for you to make to understand what neural networks are, because the individual steps of a neural network from the beginning, where the information of the feature variables enters the network until the output, so until the prediction is made with the network, is something that you already know, which is just now composed more than once in comparison to the basic models we discussed in the beginning. Neural networks surely are more of an advanced model, and surely if you want to study them in detail, this is probably something which is better suited for a master course. But I think you can grasp the idea of it, and I think it's important you already grasp the idea of it at this stage, because neural networks are so much more than just function approximators. They are also used in very different ways, in very creative ways, for instance, such things as autoencoders or general advisory networks. They are also used for making and creating artificial intelligence with the methods of reinforcement learning and so on. So there's a really big playground how and in which ways we can apply the mechanism of neural networks. Okay, but now what you want to do here. I mean, the slides, they are quite technical as always, but most importantly for you, I really want to share the idea with you. So we will try to divide this in our head into individual blocks. The first one is by an example we are going to discuss how what makes up a neural network. Then how are we building a neural network? What does it even mean, or does it mean when we talk about the architecture of a neural network? So basically the question is, how is a prediction made with a neural network? Then we also discuss the issue of calibration of a neural network, but this is not really any new stuff for you, because the ideas of the basic models, they are the same. So depending on the task you're facing, regression or classification, you choose an appropriate loss function, and a neural network simply also depends on parameters as the models you already know, and then the parameters are calibrated on the basis of training data by minimizing the loss function. And that's it. So that's all we want to do here. I just want to show you the linkage to the more easy models we discussed in the beginning of the course. And I just want to give you a short and brief introduction in a forward neural network structure. So what you should need to know is, first of all, like the wordings. So a neural network is something which consists what is called layers, and each layer has a certain amount of neurons. And as you may guess by the naming here, this comes from the wish to rebuild the mechanisms of a brain which has neurons which are activated when we do some stuff. Okay, the input layer, that is like the fancy name for describing the vector that we usually have when we have the feature information of a single sample from our data set. So I don't know, it could be the age of a person, I don't know, what it ate for lunch, and where it went to its last vacation. So this could be like the fictional feature variables, and we have for a single person 3 realizations here. So that is what is the input layer. So the input layer is basically just the original feature information which is going used as input. Then but to have a consistent naming or wording here, those are already called neurons. So what we called so far the realizations of feature variables are now the neurons of the input layer. Then from the output layer, here neural networks are kind of flexible. So far with our base models, we had 2 possibilities here. So for the regression type model and for the logistic regression model, we had a single output value for each sample in the data set. For the regression model, it is simply a real valued number. For the logistic regression model, it was a probability prediction. And for the for the multi-class regression model, so we had the softmax regression, then we had for each observation in our data set, we had more output values. The number of the output values we had was equal to the number of categories of the target variable, because for each category of the target variable we predicted a probability that the ith observation belongs to a specific category. So, and those are basically the things we also can do with neural network. A neural network can make a single prediction for each observation in the data set, but it can also make an arbitrary number of predictions for a single observation in a data set. That simply depends on us how we define the neural network, but this is what is called the output layer or the output neurons. So basically the predictions we want to make with the neural network. Then in between, so it starts with the input layer and the input neurons, which are just the realizations of the feature variables, and it ends with the predictions, which are called the output neurons, or the neurons of the output layer. But what's different in comparison to the basic models we used is that we have something in between now. So we have something what we can picture as an intermediate step, okay? And so this is what you can see here. So here you could see a visualization for a single observation in a data set. So it has n feature variables. So this is the realization of the first feature variable, this is the realization of the second, and this is the realization of the last feature variable. And assume for the moment, this does not has to be the case here. Assume that we also would have, for a single observation, we also want to generate n output values, so n output predictions. So we, you can picture it as making a prediction for each feature variable here. Doesn't need to make sense right now. If you would have a single prediction problem, so a regression task, then we only would have here a single output value, okay? And those values would not exist for a regression task. The most important aspect here is what's happening in between. And in between is what we have here is a hidden layer. This is like a single hidden layer. We could also have a neural network with 2 hidden layers, then that we simply would have another row of neurons here in between. And the only thing you really need to understand right now is how we are generate what's called the neurons of the hidden layer. So how do we generate the values that are represented by these circles here in between? And you will see that these values here in between are generated in very similar ways than we usually generated the predictions for our basic models that we discussed in the beginning of the semester. And so how you can picture it, assume now we have n realizations for the ith observation in the data set. And what we're going to do by using different parameters, we first we weight those realizations with some parameters and generate just another number. And then we use a different set of parameters in order to generate a different number. And then with these different numbers, we do basically the same thing. So with those hidden neurons, we do the same thing as we did for the basic models in the beginning. So again, we could use a weighted average of those realizations here in order to generate a single output for instance, a regression task. So this is how I would define it with my words. And I mean, you'd see, like at the slides, you can see here, this is how it is formally defined. But in the beginning, this is kind of confusing because the notation is kind of a pain in the ass, to be honest, especially in the beginning. So that is why we want to now skip to an example that I will show you on the iPad, which is basically more or less very similar to the example that you can find here later at the slides. But let's do it together step by step with the iPad, and then we will, during the explanation with the iPad, I will also, go a little bit more into detail, and then after that, we discuss the issues of how we are going, after we understand the mathematical operations within a neural network, we're going to discuss how it's calibrated, how we use the loss function, and so on. Okay, so let's go to the iPad. Okay, so I'm just going to make up any fictional numbers here. So the actual numbers that we're using in this example, they will not make any sense, but it's more or less about understanding the process which is like in a neural network, how feature information is processed through a neural network in order to generate predictions. So let us start, and let's assume we have, I don't know, 3 feature variables, so x1, x2, x3, for a single observation. So this would be a single sample from our data set. So let's really try to make it easy. So let's say this is equal to 1, this is equal to 2, and this is equal to 3. Okay, then, and for the moment we will keep it flexible, but assume that we will at the end want to make again either a regression type prediction, or a prediction for a binary, or a prediction for a multi-category classification problem. Nevertheless, all the basic models we learned so far in the beginning of the course, so the linear regression model, the logistic regression model, and the softmax regression model, they had all the same building block in the beginning, and that was like what I was referring to as the affine transformation. And the affine transformation is always something that makes usage of parameter values. Okay, so what we had here, we had the value of x1 weighted with a weighting. Let's say now it's let's not use the theta symbol, so let's use this one instead for representing a weighting. Then so each realization gets a weighting, and we had something which is called the intercept for the linear regression model. And in terms of, or when we are talking about neural networks, usually it is called a bias value. Nevertheless, these green values here are parameter values that need to be calibrated. And calibration always needs that typically we use those parameter values that will minimize a certain loss function that tells us if our predictions of the model are accurate or not so accurate. Then for the let's just delete that in order that we have a better view here. So this is really like the building block that was shared by all of our basic models. For the regression type model, we stop at this point for the linear regression model. Okay, so this is like our equation, how we're making forecasts for the linear regression model. For the logistic regression model, the only thing that we did furthermore is we used that building block here and inserted it into another function, which was, for instance, the sigmoid function. So if we plug this into the sigmoid function, then we had our probability prediction. But the important aspect here for you to understand is that we have the affine transformation and we plug it into a function. So the output value of the affine transformation is just inserted into another function. And typically, so for the linear logistic regression, this is a function that needs to have a value range for its output values that refers to probability value, so which needs to be between 0 and 1. But obviously, of course, like from a mathematical perspective, we can use any function here. And yeah, for the moment, let's just not go to the softmax regression. Now we have all we need to know how we are going to generate neurons in a neural network. So what a neural network basically does is exactly those two operations in order to generate a single neuron. And if we wanna, if we want to generate more neurons, the only thing we need is more parameters. So let's write this down one more time. So if we, for instance, want to use our data here, and let's assume that this is like the transposed vector of our input from the featurables, then we could use as above, first of all, we could generate a number, for the moment a fictional number, by using weighting parameters. So let's already write this down in a matrix, but it could be something like this, okay? And so if we, when we're doing matrix multiplication, then what would result here is obviously x1 times the first parameter plus x2 times the second parameter plus x3 times the third parameter. And then we could also, of course, add a bias term. And this is, what would result here. Let's call this for the moment Z1, okay? So that is what results in Z1 here. Now, as you already see what I'm starting here, if you want to generate another value that is different from Z1, then all we need to do is use different weightings here, for instance, that are given here in a second column of this matrix. So let's do this. So basically all the same, but the weightings are different here. And we add another bias term, and that generates our second value here. Okay, let me just rewrite that because it looks really ugly. Okay, so basically when we want to calculate the first one here, what we're doing here is we make the matrix multiplication with the first column and add this number, and this results in Z1. And for the second value, we again multiply this one with the second column, add this one here, and get this value. Okay, because we have just to make sure, we have a 1 times 3 matrix, which is multiplied with a 3 times 2. So that results in a 1 times 2 matrix, and we add a 1 times 2 vector. So please excuse me my writings here. So if we really want to make this formally correct, then we would need to write it like this, and that results in those two observations. It kind of got confused here a little bit because typically one writes the weighting matrix first and then the other vector, and then we have the dimensionality as I described in the beginning. But if we want to make it consistent here, then we have a 1 times 2 matrix that results from this matrix operation, and we add element wise the vector of the bias terms here with the 1 times 2 dimensionality. But most importantly, beside all this mathematic notation and all the formalism here, what's important for you right now is that we generated 2 values now out of the 3 feature input values. And obviously, and I hope you can really follow here, if you would have want to create 4 values or 10 values, the only thing you need to do is to add further columns here. So this is like in further columns here means just you adding more and more weights. So that means your model will need to estimate more and more weights. But by this way, you also are able maybe to derive more information or get more information out of the original input information, which is presented by the X values here. Okay, but let's just go with this example here. So what we do here, you may imagine that instead of directly, making usage of a regression model, so of a linear regression model, what we do here is we condense the information of 3 numbers, which are the input information, into 2 numbers in an intermediate step. Okay, and now, so far, if we use the Z values here, we still are stuck to affine transformations. And affine transformations, like these operations given here, they only relate to, or they are only able of capturing linear relationships. So, relationships which something look like this. In reality, we may have, for instance, relationships that look like this, or even more extreme ones that look like this or something, okay? And this is where it really starts to get very interesting when we're using neural networks, because neural networks, as I said in the beginning, they are capable of, capturing almost any functional relationship. So even like the rather complex ones that I draw here, okay? Or at least also the nonlinear ones that I draw here. And they are able to do so because that we do not usually stop with those set values. We do one more thing, and that is we use a nonlinear transformation of those set values. And here this is kind of arbitrary. So the function we are using here, it can be chosen by us, okay? That can be chosen. And you can see in the slides that there are different, possibilities. Common choices are also, even though we do not use this directly for a probability prediction problem, for instance, the sigmoid function again, but there is like the tangents hyperbolicus function, I think is how it's called in English, or the ReLU function, which is the rectifier linear unit function, or the CeLU or the ELU, and there are more and more and more, and I think the more popular neural networks become, the more we will learn about new and other activation functions. So, but the most important part for you is here that we use those values that are given here, the Z values. And once we have certain parameter values, it is obviously kind of easy to calculate the Z values because this is basic matrix calculation. So we need the matrix multiplication of the input features with the weight matrix, and we need, to add to this vector some bias terms. And when we have 2 numbers representing a condensed version of the information provided by the feature variables. And now we can choose any, function. So each of those set values is now inserted into any function. And typically it can be chosen, this function, but especially what's very helpful is it is, chosen in order to capture non-linear relationships. And that can only be done if we use a nonlinear activation function. Okay, so usually a nonlinear function. And if we plug the Z values into this activation function, so that's how it's called usually, then we get what is called the hidden neurons or the neurons in the layer. Okay, so these are then really those 2 values. And this is how you are able to, generate an intermediate step, or to introduce an intermediate step for making predictions for regression tasks and for probability prediction and so on and so on. Because now what you can do, in our example, we have a single hidden layer with 2 neurons now. So the input is given here by the feature variables. So we have 3 feature variables. And now in the first step, the information of the 3 feature variables is condensed into 2 hidden neurons. So that is where we are at this step. The step from the feature variables to the hidden neurons is made by combining the affine transformations and nonlinear functions. So basically the same thing that we did for a linear regression model or for logistic regression model. We have an affine transformation in combination with a function. For the linear regression model, the function here is the identity function. For the logistic regression model, we have typically the sigmoid function here. Okay, and now if we stick to one hidden layer, obviously what we can choose here, and that is why we are talking about an architecture and something we are defining, we are creating. We choose the amount of hidden neurons by specifying the weight matrix, and especially by specifying the dimensionality of this weight matrix, because as many hidden neurons we want to generate, as many columns of weighting parameters we need here. But this is something we can define. Also something we can choose is which activation function we are going to use here, and we can try out different activation functions. And now what we can do, you could either do the same thing again with a new set of parameters and with a new set of an activation function in order to do the same thing what we did in the previous step with the feature variables can now be done with those hidden neurons in order to again generate new hidden neurons, right? That would be the case if we want to have a second hidden layer. But obviously what we also could do now is treat those two values as in the same way as we treated the original feature variables for our basic models. So if we have a regression model or we have a regression task, then we could use another, we could use a weighting again here. So let's do it like this. Let's make the usage of this 2 number here. So it stands for the second weighting transformation that we use. We could choose another weighting here. And we could use a bias term here. And this would be our, regression type prediction that you generated with our forward neural network. Because we started with 3 feature variables. By applying affine transformations and a nonlinear activation function, this was transformed into 2 hidden neurons, so 2 neurons from a hidden layer. And those 2 hidden neurons, they are then used in order to make the prediction. So this is how our neural network would look like. So here we would have x1, x2, and x3. Then, it's generated the first hidden neuron by weightings for the 3 feature variables, adding the bias term and activating it with a certain function. The same was done for the second hidden neuron. Okay, so this is what's indicated by this. And then the information of those 2 neurons is again, merged in order to make a single prediction. This is how our model looks like. And of course, and I hope you can guess that, if you want to make another regression type output here, so if you do not want to make a prediction for any real valued number, if you just want to make a prediction which resembles a probability, so for instance for a binary classification model, then you would do the same thing here, but you will use the sigmoid function of this weighted scheme of hidden neurons. So this is what we would calculate if we would have a binary classification problem. And I'm not writing this down because maybe it gets too confusing, but if we would have a multi-class classification problem, then we would need more weightings here. We would need as many weightings for the output prediction in order to generate a probability prediction for each category of the multi-class classification problem. But that is like the same as you would need to know for the softmax regression problem. So, and I hope at least this makes it a little bit clearer that what I was referring to when I mean that you already have the knowledge in order to understand the neural network structure, because it makes usage of the same things you already know. It makes just usage of these affine transformations and combines them with nonlinear activation functions. And while, for instance, for the logistic regression model and the softmax regression model, we only did this one time directly with the feature variables, the only difference for the neural network is that we do this more often. So we do this, for instance, here 2 times. So in the first step, we do this 1 more time in order to generate the hidden neurons. And then in the second step, we do this to generate predictions out of the hidden neurons. But the things we do in between is always the same. It's always the affine transformation, meaning we have the weightings of neurons plus a bias term, and then some transformation of the value that is generated by this affine transformation. Okay, even though it still may sound complex, even though it still may look complex, this is what I would be happy if you understand. So if you are really struggling with this and understanding that this is basically the idea of using like these weighted averages and inserting those in functions and then making predictions. So combining always those affine transformations with nonlinear activation functions, please do not hesitate and contact me and tell me what your problem is, and hopefully I may again be able to explain it to you. If you're just struggling with the notation here, of the formalism here, then do not worry about this. This will get more clear the more often you are forced to really understand the formal notation here. But for the moment, I would be happy if you really understand the idea, what's meant if you take a look at this visualization here. That would be completely fine, to be honest. Okay, so starting from the input here and ending in the output is what is called a forward pass. Okay, and now we are at the position where we hopefully understand how we can build neural networks. So that means they depend on things that we set as users. So the decision how many hidden layers we want to have, the decision how many neurons we want to have, the decision of how which activation functions we want to use. And for instance here, like just to give you an idea, those are, for instance, kind of popular activation functions, but there are more, and it's your choice. And yeah, but hopefully now we are at least at the point where you understand that how we can generate predictions with neural networks. And hopefully you also understood that neural networks are made for any kind of task that we discussed so far when we're talking about prediction tasks. So it can deal with regression tasks, it can deal with binary classification tasks, it can deal with multi-class classification tasks. The only thing which is defined by the problem at hand is what you need to make sure how the output of the neural network looks like. So if you have a regression task, then usually you use just the affine transformation from the last hidden layer to the output. If you have a binary classification task, then you kind of are forced to use the sigmoid activation function from the last hidden layer to the output. And if you have a softmax regression model, then you need to choose the softmax activation function in the last layer. But except this, everything else can be defined in the way that you think is best. Or this is also, like a process which is then called later hyperparameter tuning, finding good, the architectures of neural networks. But yeah, that's like for the moment, the most important part when it comes to the question is, what is a neural network and how can we make predictions with a neural network? In the next video, we are going to, dedicate ourselves in order to rediscuss how the parameters of the neural networks are estimated. This is going to be a quick one because the current answer is, and it will not change in the same way as before. So no really big news, but we also will discuss some, hands-on specifics when it comes to the usage of neural networks. I will also quickly show you how a neural network can be defined with your Python program using a API which is called Keras. And we also discuss some other specifics in this context, which refers to overfitting. Okay, but this is going to be done in the next video. So see you there and hopefully soon. Bye bye.